Hello, my name is Todorov, and I'm going to present to you an introduction to the Deal Poly software project. I'm the lead developer of Deal Poly at the Scientific Computing Department at STFC Tarzan Laboratory in the UK. This lecture is filmed at NCSA Bulgaria. So, Deal Poly is a general purpose parallel classical macrodynamics simulation software. It was conceived to meet the needs of CSP5, which is the computer simulation of condensed phases community, and it is written in modularized Fortran 90 with MPI2, and it's fully self-contained. There are two packages within the Deal Poly project, Deal Poly 2 and Deal Poly 3, which in 2010 moved to Deal Poly Classic. Deal Poly 2 moved to Deal Poly Classic on a BSD open source license, and Deal Poly 3 was up licensed to Deal Poly 4. Deal Poly Classic was developed by Bill Smith and Tim Forrester starting in 1994, and Deal Poly 3 started in 2003 with me as a lead developer, and now as Deal Poly 4 I still lead that package. It is free of charge to academics, but at cost to industry. Overall, there are about 16,000 licenses taken out since 1994, and over the last 4 years, the average has been around 1,600 annually. And there are about 1,300 registered forum members since 2005. The current versions are Deal Poly 4 version 5 and Deal Poly Classic version 1.9. The difference between the packages is the principles on which they are engineered. In Deal Poly 4, we rely on domain decomposition parallelization, which is based on static domain decomposition, so we don't have dynamic load balancing, and it's got limits up to about 2 billion particles. It's got parallel I/O with options for NetCDF, and it's got some specific radiation damage features. It is quite flexible. It's got free formatting, free format reading with some fail-safe features and basic reporting, but it is not fully foolproof. Deal Poly Classic, on the other hand, is based on replicated data parallelization, and it's got some limits due to the drawbacks of that parallelization strategy. So it should be used up to 30,000 particles and to up to 100 processors. However, it includes some advanced features like hyperdynamics, temperature-accelerated dynamics, and solvation dynamics. So let's refresh ourselves on what macrodynamics is about. In a nutshell, there are some very strict definitions here. So it's a theoretical tool for modeling the detailed microscopic behavior of many different types of systems, including gases, liquids, solids, polymers, surfaces, and clusters. In molecular dynamics simulation, the classical equations of motion governing the microscopic time evolution of many body systems are solved numerically, subject to boundary conditions appropriate for the geometry of or the symmetry of the system. They can be used to monitor the microscopic mechanisms of energy and mass transfer in chemical processes and dynamic properties such as absorption spectra, rate constants, and transport properties. It can be employed as a means of sampling from a statistical mechanical ensemble and determining equilibrium properties. These properties include average thermodynamic quantities such as pressure, volume, temperature. People can look at the structure and phase changes or calculate free energies along reaction paths. So people ask base questions when they use this methodology. For example, can I follow the motion of a single molecule in some media, like in a glass of water, for example, or investigate phase changes, like in sodium chloride. Or they can try to improve their understanding of how complex systems behave, like polymer melts, for example. One of the simplest simulations one can think of is presented here. This is a box of argon, where argon atoms interact via simple Lennard-Jones potential. In the next slide, I'll show why we have a cutoff. Within the cutoff, this atom interacts with all the atoms within, and it doesn't know anything about the ones outside. We can write the Lagrangian of this system, which is simply the difference between the kinetic and the potential energy. So this is an example of what the Lennard-Jones potential looks like. So we have a hard sphere-like behavior at short distances, so atoms repel, and at long distances they attract each other. We have to cut the calculation of the potential and the force at some distance, because it would be prohibitive otherwise to use on a computer and calculate those. Of course, we have to choose wisely the cutoff distance so that there is no discontinuities in energy and force at those distances, so that the potential should decay very, very quickly and it should be as close to zero as possible, the cutoff distance. Of course, the interactions are pairwise radial, so this is the distance between a central atom and other atoms, and this is the potential. So when we solve the Lagrange equation and look at the time evolution, for this simple system, we arrived at the Newton equation, mass times acceleration equal force. So the computational work that we need to do is to calculate the forces in all atoms, and then do the integration of the system where we allow atoms to move according to their velocities and forces. We can have, in simulations we have boundary conditions. For certain cases we don't need any boundary conditions, so we have a polymer in vacuum, or in some infinite media that doesn't interact with itself. In certain conditions, we need to have stochastic boundaries, for example, for polymer simulations, or hard-wall boundaries for pores or capillaries. And quite often, we have periodic boundaries. One of the reasons to use periodic boundaries is to pretend, because the simulation cells that we look at are fairly small. Even if we reach millions of atoms, this is still a very small number with comparison to the Avogadro's number. Therefore, in order to pretend that our system is infinite, we have to employ periodic boundary conditions. And here there is a simple example of what these are. If you have a box with a number of particles, this box sees itself in all directions. This is a 2D cubic periodic condition. So a replica of this particle is situated here, and a replica of this particle is also situated here. When these two particles interact, it is as if these two interact, and so on. There are a number of periodic boundaries that can fill up the 3D space uniformly, and these are the 4 different ones. We can have a triclinic periodic boundary condition, a hexagonal prism periodic boundary condition, truncated octahedron periodic boundary condition, and rhombic dodecahedron periodic boundary condition. What comes out as a result from molecular dynamic simulations are certain properties, so kinetic energy, temperature, total configuration energy, pressure, specific heat. There's some structural properties that can be calculated in this plate, like pair correlation or radius solution function, structure factor, which of course is something that can be compared to experiment because it comes out from experiment from X-ray neutron scattering. And there are correlation functions like the mean square displacement, velocity autocorrelation, and there are some collective correlation functions like the general Van Hoof correlation function and the derivatives, the Van Hoof self-correlation function and Van Hoof distinct correlation function. Of course, these don't come naturally from the modeling software, but one can use the dual poly GUI to obtain those. So let's look at what the essentials of dual poly and algorithms are like. Dual poly, as presented on this slide, can simulate any mixture of those quantity identities presented here. So we can simulate point atoms or ions. So the particles can bear a charge. We can include polarizability if we have two particles and say they behave like a core and shell, we can have flexible molecules presented by bonds, angle dihedrals, and so on, or we can have rigid bonds, which are in fact constraint bonds. This is a nice concept to use if you wish to avoid vibrations in certain systems, because then that limits the size of the time step during the integration. And if you want to get faster to solution and these vibrations are not essential, then we use constraint bond algorithms. And if you want to reduce the degrees of freedom, if it's not important how, for example, water vibrates, then we can rigidify that molecule. So we can use rigid molecules, and rigid molecules have only 6 degrees of freedom, 3 for the move of their center of mass, and 3 for the rotation around 3 different axes. And of course, rigid molecules can be connected by flexible links, or they can be connected by rigid links. And of course, this functionality is limited only to dual polyclassic. So in previous lectures, we have talked about force fields. Let's give some strict definitions about the identities in the dual poly field file. Essentially, a particle is a rigid ion or an atom. It is charged or not, and it can be a core or a shell of a polarizable ion. It can also be a massless charge site in a rigid body. A particle is always a countable object and has a global index corresponding starting from 1 to as many particles as we have. A site, on the other hand, is a particle prototype. One can think of a site as the stoichiometric definition of the compound. So if we have, let's say, 10,000 molecules that we say we have in our systems, we actually have only 3 sites for each molecule if each water molecule is the same and contains 2 hydrogens and an oxygen. It's a particle prototype that serves to define the chemical and physical nature of a particle. So it has mass charge, some state of whether it's fixed on space or not, which I call frozenness, and it can define the topology or stoichiometry, connectivity of the molecule. So sites are not atoms, they're just prototypes. Of course, we also have intramolecular and intermolecular interactions. The intramolecular interactions, such as chemical bonds, bond angles, dihedral angles, improper dihedral angles, inversions. Usually the members in such an interaction do not interact via an intermolecular term. However, this can be overridden for some interactions. So these are defined by site. The intermolecular interactions, such as van der Waals and metal interactions, Tursuv, 3-body, 4-body, and so on, they're defined by species. So if we say we have a water molecule with H standing for the hydrogen and O standing for the oxygen, we can define the intermolecular interactions, which would be van der Waals, as between O's and H's. However, when we define the intramolecular, how these 2 hydrogens and an oxygen interact within the molecule itself, these have to be defined by site. Of course, we also allow for electrostatics when we have interaction between charged particles. There are various methods within dual poly packages. We have standard E-Vault, or Hotman-Klein E-Vault, which is aperiodic in one direction for slab simulations. These are only available within dual poly classic. We also have SPME, split particle mesh E-Vault, which relies on 3D FFTs for the correct E-Vault summation. And we have some approximations, such as force-shifted Coulomb reaction fields, phenol damped reaction fields, distance-dependent dielectric, and we may account for non-charged neutral MD cells by using the Fuchs correction. We also have ion polarization, as I mentioned 2 slides earlier. This can be solved either by a dynamic or relaxed shell model. The difference is in the dynamic shell model, the shells are moved according to the Newtonian equation of motion. They have to have some mass, which has to be a very small fraction of the mass of the full ion. In the relaxed shell model, they don't need to have mass, and they're solved using conjugate gradient methodology, relaxing the total gradient of all the shell forces to a very small number. If the user chooses to use the dynamic shell model, they have to warrant the adiopaticity of the system, so there is no transference of kinetic energy between the shell and the ionic system. Diel poly also allows for the usage of external fields such as the electric, magnetic, gravitational, and there are some other fields as you can see on the website. And there are some intermolecular-like interactions. I already mentioned that we have rigid body units and polarization. These are called intermolecular-like because they are defined by site. The constraint units, I talked about the KMF units similar to the constraint units, but the members of that rigid bond do not need to be in a chemical, do not need to be in a close proximity and to be in a chemical bond themselves. Of course, all the potentials for those interactions provided us various analytical follows with the Diel poly. They're parameterized, and it's the user responsibility to provide the correct parameters for the specific interactions. And Diel poly only takes spherically symmetric interactions. There is one restriction on all these identities. We cannot change the chemical nature of particles in space and time. Essentially, what it means is we cannot break bonds or create bonds. Of course, this can be counteracted by specific force fields like relax FF. However, this is still not available within Diel poly. The full force field of Diel poly can be presented as this formula. We have three different kinds of interactions. We have the intermolecular, the intramolecular, and the external force field. So the intermolecular pair, coulombic, tertiary 3-body, 4-body metal interactions. These are defined by type of particle, and the rest with the exclusion of the external force field defined by site. So what we have, as I mentioned, we have pair. This is again pair but long range, the coulombic interaction. Tertiary is a mixture of 2- and 3-body interactions. In other packages, there are Stiligen-Weber interactions, which are again similar mixture. We have pure 3-body, pure 4-body interactions. We have metal interactions. A few slides back, you may have seen that we have different metal interactions. So we have Sutton-Chen type, Finis-Sinclair type, Gupta. We also have such that are not defined by functional forms, such as the embedded atom model, and there are some extensions of it, the extended embedded atom model, and the two-band extended embedded atom model. The metal interactions, in principle, are environmental dependent. They're many-body, but they can be decomposed in a 2-body form and a density-dependent form, a density-dependent term. The boundary conditions that the Diel poly packages take are none. So we have an isolated micromolecule, cubic boundary conditions, orthorhombic boundary conditions, parallelepiped or triclinic periodic boundary conditions. The two fancy ones, truncated octahedral periodic boundary condition and the rhombic dodecahedral periodic boundaries, are only available within Diel poly classic. And of course, we have slab periodic boundary conditions, which are aperiodic in Z direction. So the Diel poly software, both Diel poly classic and Diel poly 4, rely on a simple concept. Even though modern parallel computers are much more complicated than this simple scheme, we still rely on this concept that we have a congregation of processors, each of them having their own access to their own memory, and we presume that all processors have the same power and the same amount of memory, and they communicate between each other without any specific directionality. So Diel poly is designed for homogeneous distributed parallel machines. However, specific implementations may rely on specific parallel machines like such that have graphic cards as accelerators. So we have a CUDA port, and then matters are slightly more complicated. However, for the purposes to demonstrate how the algorithms within deal poly work, we shall assume that this is the simplest architecture on which we base those. In deal poly classic, we use replicated data strategy. So if this is the general MD cycle, where we have some initialization stage, then we calculate forces, do motion, gather statistics, and repeat this until we are satisfied, and then we produce a summary. This cycle is replicated on all four processes presented here by the letters A, B, C, and D. So all processors initialize the data on them, and they split the workload on the forces, and they split the motion, and they split the statistics gathering. But in order to be back in sync together, they have to communicate, because in order to do the motion, you have to have the particles in all forces. And the drawback of this methodology is that the system, each processor knows everything about the system, and the larger the system, the more we need to communicate in order to sync up the data on all processes. And this is described in this slide. So if the system is presented by this box, every processor sees the full system, so there is no memory distribution. The performance overheads due to that and limitation when increasing the system size. And the decomposition between the decomposition of the interactions is always functional. So it depends on some algorithmic division. Of course, one of the beautiful things about this scheme is that your cutoff can be as big as the half cell width, which is not the case for the domain decomposition strategy. And of course, when we go to very large processor counts, we will suffer extensive global communication. In order to calculate the pairwise interactions in the replicated data strategy, we have to split the work in some smart way between processors. And here in this slide, we show this table which outlines how interaction between 12 particles, all possible interactions between 12 particles can be split on 4 processors. If we enumerate all possible interactions and go this way and then fill the next row and so on and so forth, we can then divide this table in a manner that every fourth row goes to processor 0, so starting from 1 going on processor 0, then row 5 goes on processor 0 again, row 2 goes on processor 1, and so on. In this manner, all processors will have nearly the same amount of work. And this list can be distributed, and forces due to pair interactions can be efficiently load balanced. The calculation of those forces can be efficiently load balanced. In domain decomposition, which is the polarization strategy on which deal poly 4 is based, the situation is very, very different. So we have 2 packages, but underneath the hood, we have 2 very different engines of how we distribute work between processors. Again, we look at 4 processors and how we split the system on it. Let's imagine, for the purpose of this demonstration, that is, we have our system is 2-dimensional. So the work is split between A, B, C, and D, and our MD cell is divided on these 4 processors. So this is the MD cell. So each processor takes the same amount of bulk of the system, or has the same amount of volume. And there's a finer mesh on this sketch, which have a size of the cutoff. And later on I'll demonstrate what the significance of that is, but essentially if you have a particle in this box, it can only interact with particles in the nearby neighbors of it. If we're in 3D space, then we can see what it looks like now. Our system has 8 processors, and this is the finer mesh of what we call link cells. in order to have the system contiguous and all processors to know everything about everything, we need to send something that is called halo, and here this is demonstrated by the blue bands around. In order to complete the calculation of two-body forces, if we have a particle that is in this box on processor A, and it interacts with some neighbors that on processor B needs to send data to A and A to B in order for particles near the boundaries of those domains to know a little bit just outside. And that information we call halo. So our communication in this approach is only between nearby processors. So it is not global, it is local communication. It's limited by the size of the cutoff, or rather by the ratio of the size of the domain by the cutoff. So as I mentioned in the previous slide, we use something like link cells, and link cells provide very nice functionality. We built link cell lists, which are an elegant way to scale short-range two-body interactions from point square to ON. And the efficiency increases with increasing the link cell partitioning. So the more link cells we have, the faster we process this. As a rule of thumb, the best efficiency is achieved for cubic-like partitioning with the number of link cells per domain larger than 4. Essentially, when we build the link cells, we use some time, which we call a prefactor. In order not to fill this prefactor, we have to have a number of link cells per dimension that is larger than 4. So link cells can also be used for 3 and 4 body interactions, and they're even more efficient because 3 and 4 body interactions have a shorter cutoffs. And because we have shorter cutoffs and it's the same size of domain, we have a finer mesh that's imposed on those domains. And as I mentioned, again, the more link cells we have per dimension, the faster this search algorithm works. Essentially, the larger the particle density or the smaller the cutoff with respect to domain width, the shorter the Verlet neighbor list searches. And this is how the link cell list works. Essentially, all particles are qualified in link cells, and each link cell has a head of chain list and a link list. And when we start the search of all possible pairs, for example, we start from this number 6, so particle 6, and we look what particle 6 interacts with, and we can see that particle 6 interacts with 10, which is displayed here, and 10 is the element that is in the link cell list with number 6, so this number corresponds to the particle number. And if you want to find out what is the other particle 6 interacts with, we have to jump from this element to the next element, which is with the number of the previous element. So we jump here to 12, which is the 10th element, and then from 10 we jump to 12, where we have 16, and then from 16 we jump here, and it is 17, and because in 17 we have nothing, we have to come back to the head of chain list. Repeating this procedure offers this elegant way of generating all the two-body interactions in a list called Verlet list, which can be used very, very efficiently for the calculation of the two-body forces. Of course, this concept of link cell list can be improved. So now, imagine that this link cell depicted here is actually this size. We can impose a finer mesh. And for example, if we have a particle here in this link cell, we know that this particle only interacts with particles that are in the finer mesh that are contained in this sphere. And essentially, instead of looking for all particles outside that sphere and losing time, we can make this more efficient, and we can gain some performance, which theoretically is about 45%. But in practice it's about 30% because we complicate the search. So how do we compute the bonded forces? So as I explained, it's an algorithmic decomposition, interacted and managed by bookkeeping arrays. We have explicit bond definitions, and we have shared bookkeeping arrays because we have processors, and sometimes we need to know how bonds are shared between processors. The non-bonded forces, we use a distributed Verlet neighbor list, which is used for the calculation of the pair forces. And we also use link cell lists for 3 and 4 body interactions. The implementations of those arrays and algorithms actually vary between DL Poly 4 and DL Poly Classic. And we will show how and why they need to vary. For example, in DL Poly Classic, it is very simple to count the bonded interactions. And here this is represented by this graph, because we can cut them if we have 10 bonds and 4 processors. We can start bond 1 on processor 1, bond 2 on processor 2, and so on. But because of domain decomposition in DL Poly 4, this is impossible, and it is quite complicated to do all this bookkeeping. So it is a demonstration to follow here on the slides. If we just account for particles, it is for replicated data is fairly simple. All particles are distributed on different processors. While with domain decompositions, particles are spatially distributed. So here we represent one domain. If we have bonded interactions, as I said, it's very easy to distribute them because we can cut them and start distributing them between the various processors just by their number. In DL Poly 4, due to the domain decomposition, if we have the same chain, then the situation is complicated, and all this part of the bond interactions will lie on processor A, and there will be a small bit that lies on processor B, and the rest will be lying on processor D. So it is not fully load balanced, but the relative cost of bond interaction is very, very little with respect to non-bonded interactions. However, the complication here is that we have to keep track of all the bookkeeping, because as the dynamic proceeds, some of those bonded interactions will come to this processor, some may come to these processors, and we have to have very, very strict bookkeeping. That is why we show this picture. The actual bookkeeping is very, very tricky in domain decomposition. In order to do the motion, we employ a number of integrators in DL Poly. So we have two types of couching the integrations of motion. We have velocity Verlet and Leapfrog Verlet. And the user have access to the following ensembles. So we have the microcanonical here, we have the isokinetic of events, we have the canonical in various interpretation, we have Anderson, Langevin, Berenson, Musée-Hoover, and gender stochastic thermostat. We have the isobaric and isothermal ensemble, again various interpretations, Langevin, Berenson, Musée-Hoover, Martino-Tuckerman, and Klein. Here we have the anisotropic pressure and constant temperature ensemble, which can be extended to those fancy ones for interfaces and slabs, which have normal pressure and surface, or preserve normal pressure and surface tension. Again, these come in various flavors, such as Langevin, Berenson, Musée-Hoover, and Martino-Tuckerman and Klein. And as I mentioned earlier when I talked about the force field, we also have constraints and rigid body solvers. These are on top of the particle dynamics. For the velocity Verlet dependent algorithms, we have rattle and no squish for the rigid bodies. So rattle is for the constraint solvers, no squish is for the rigid body solvers. And if we have rigid bodies with constraints, we have Q-shake and DL Poly Classic, only available in DL Poly Classic. The correspondent algorithms in Leapfrog Verlet are shake, the Euler-Quaternion, and again the Leapfrog Verlet shake, Q-shake. So the essential requirements of the integration algorithms are computational speed, low memory demand, accuracy, stability, which is often interpreted as a good energy conservation, no drift in energy. And it is a very useful property to warrant the time reversibility. And even better if they're symplectic. Symplecticness means that they're not only time reversible but have long-term stability. And most of the velocity Verlet derived algorithms are symplectic, especially those of Zechov, Martino-Tuckerman-Incline, and the gentle stochastic thermostat. The simplest representation of what integration means is, especially in the microcanonical ensemble, is propagating from a point in time t to t plus delta t, where we propagate position, velocities, and forces. And the move of this example particle here have a net displacement coming here at time t plus delta t, which is a sum of the one contributed by the velocity of this particle at the moment t and the force on this particle at the moment t. As I mentioned, this is this is the general MD cycle, and we have two types of couching of the integrators. We have the Leapfrog Verlet, which is the default in dual poly classic, and we have the velocity Verlet, which is the default in dual poly 4, but both of them are available if this is specified by the user in each of the packages. This is a representation of the Leapfrog Verlet. This is what the application of 18 practices, but these are the actual two equations. The difference between the Leapfrog and the velocity Verlet is that the velocity is half a time step displaced with respect to the force in the position. And that is why we have this small third step here, where we average the half time step ahead and half time step behind the velocity in order to receive, to estimate what the exact velocity of the time step is. The velocity Verlet integration algorithm is somewhat simpler. Again, we have 3 stages, and we have a middle step between the two where we have to estimate the half time step velocity in order to obtain the position at t plus delta t. And then we have to calculate the forces afresh, and we update the velocity to the full time step. And here, as I mentioned previously, when compared to the Leapfrog Verlet, we all the phase space quantities are updated at the same time. So forces, positions, and velocities. A few words about the constraint solvers. As I mentioned earlier, in order to reduce the vibrations of bonds, we can impose rigid bonds, so particles should move together so that the distance between them is preserved. It is very simple to apply this concept. Initially, when particles move, they move freely, and after they have moved, we can calculate retrospectively what the force on them should have been at the beginning, so that when they move again, fictionally they come to the same distance, and we can apply this retrospectively so that within a certain tolerance, all the bonds within the system have moved together at the default distance given between them. The situation is slightly more complicated in the velocity Verlet. So this was Leapfrog Verlet, where we have the rattle algorithm. The first part of rattle is exactly the same as shake, and the difference in the force is just a factor of 2, as you can see between these two formulae. But there is a second stage in rattle, because the velocity Verlet is 2-stage integration. The first stage is half time step velocity and full step position, and the second stage is when we calculate forces afresh in order to have a full time step velocity. So in the second stage, the summary velocity of the two particles in a bond is augmented so that the velocity component along the bond is minimized, which will help Again, the next stage would be the rattle stage, because then the bond, when particles move freely, won't move very far apart. Particles won't be very far apart when they move. There's a certain care that needs to be taken in the replicated data shake, which is because bonds are divided by particles. Essentially, we have to account for two bonds being solved in two processors, driving a particle in different directions, so we have to sum up and divide when a particle is divided in that case. Extended ensembles in velocity Verlet casting. It is worth mentioning that velocity Verlet integration algorithms can be naturally derived from the non-commutable Liouville evolution operator by using a second-order Suzuki-Trotter expansion, which guarantees their simplicity. And so all of this ensemble will have a conserved quantity warranting the conservation of the phase space volume and their time reversibility, as well as long-term numerical stability. It is quite simple to demonstrate. Essentially, the velocity Verlet algorithm shown 3 slides ago. Here consists of two parts. This is the first part and this is the second part. When we calculate the velocities afresh. So these two parts are now demonstrated on this slide. So we have the first part and the second part, starting from moment in time t and moving to moment in time t plus delta t. And in the first part, if we remove the thermostat and barostat and of course rattle, we arrive at the same equation as shown a few slides back. If we include the thermostat, then we don't have a barostat, so these two will collapse as well. These two will collapse, and instead of applied for a quarter of a time step, they will be applied for half a time step. If we include the barostat, thermostats are applied around the barostat step for a quarter of a delta t, while the barostat for half a delta t. So that at the end, the sum of time the barostat has been applied for the system is full delta t, for the thermostat is still full delta t. Here we have the two stages of rattle, the R stage, which is similar to shake, and the D stage. And the rest of the algorithmic equations are the same. So what is the base functionality? We described briefly all the algorithms within DL Poly and how these are parallelized within the different packages, DL Poly Classic and DL Poly 4. So the base functionality is that we can do electrodynamics of polyatomic systems with various options to save the microevolution trajectory at regular intervals. We can optimize structures starting from some crude configuration. We can use either conjugate gradient methods or zero Kelvin annealing. So this is not strictly electrodynamics. The conjugate gradient would be electrostatics, for example. And the zero Kelvin annealing is a very clever approach by which we can approach equilibrium safely. We can calculate various common thermodynamic properties such as temperature, pressure, energy, enthalpy, volume, and we can have statistics on them and look at their fluctuations at the end. We have options to specify what to calculate at certain intervals of time, for example, such as redistribution functions and z-density profiles. And we can do temperature scaling or velocity regaussing, and of course we can use force capping if we start from a configuration that is not very good. This is in conjunction with the optimization procedures. And of course there's much more functionality, but because of the divergence between DL Poly 4 and DL Poly Classic, we have some special features because DL Poly 4 scales to large processor counts quite well and can be used on very large systems. There's some specific features that I have developed over time, such as radiation damage defect analysis, boundary thermostats, volume expansion, replay history, variable time step, and there are some extra ensembles that don't exist in the DL Poly Classic, like Langevin, Anderson, Martino-Tuckerman-Incline, and gentle stochastic one. There's also infrequent case-space event evaluation, direct evaluation of the Van der Waals and metal potential and forces, and we have parallel I/O And DL Poly Classic, on the other hand, there are some specific methodologies that go beyond molecular dynamics. So the hyperdynamics that can be either bias potential dynamics or temperature accelerated dynamics. The latter using making use of the nudge elastic band. We also can simulate energy decomposition of solvation, spectroscopic solvent shifts of energy of solutions. And of course we have metadynamics where we can push the evolution of the system towards the desired state based on certain order parameters. So far so good. We talked about the various algorithms and parallelization strategies and basic concepts within the DL Poly software. However, in order to run the machine, we have to provide some input files and read output files in order to later on work on the data and produce graphs or films. So, what are the I/O files within DL Poly? I will be presenting only about DL Poly 4. The files are fairly similar in DL Poly Classic. If they don't exist, I'll mention this. So this is the file diagram. We have input files on the left side and output files on the right side. Those with asterisks are optional. In order to run a system, we need minimally we need 3 files. We need config that contains crystallographic and some dynamical data, control that controls what will happen during the simulation, or whether there will be a simulation, and a field that contains the force field and the particle stoichiometry and topological interactions. The optional files will be the table one, WEM, reference, and revolt. So if the potential forms not available within DL Poly for two-body interactions, or the interactions themselves can't be fitted to a potential form, this can be put in a tabulated form in the table file, and in field there'll be a hint given that certain interaction should be read in the table file. Similar for metal interactions, these that don't fall within analytical expressions, like the embedded atom model and its derivatives. There is a tab EAN file, and for radiation damage there is a specific file called reference. If we want to carry out a simulation beyond a certain time, when we want to restart a simulation from a certain point that we have previously run, we need to provide a revolve file, and we need to indicate in control that this is a continuation from a previous run. The output files on this side, so we have refcon, which is the final configuration, where we finish with the simulation. We have an output where we have some running summary data, like what are the instantaneous properties, temperature, pressure, energy and energy components, running and averages. And of course, at the end of output, we will have a statistical summary with the fluctuations. The history is an optional file. It is an incremental file of frames similar to refcon. So we can later on display the evolution of the system using some visualization software. Of course, if the user wants this file produced, they have to opt for it in the control file. There is a defects file. This is a radiation damage driven feature file, which instead of displaying the full system only displays the defects that we find in the system using specific functionality. So the file is much smaller than history, and again it's incremental. It includes the frames, but these frames are much smaller than having the full information about the full system. We have mean square displacement and instantaneous temperature file called MSDTMP. The status file, this one is optional. The status file includes all statistical data, which is dumped on regular intervals of time. The regularity, or the frequency rather, is again specified by the user in control file. or there is a default each 10 time steps. CFG min is a file that only appears if we use conjugate gradient minimization, and it contains the configuration with the lowest energy that has been produced during the simulation run. RDF data and ZDN data are the RDF data, or Z density data, and together with refcon there is a revive file. Revive is the only file that has the information in binary. Refcon and revive, of course, can be used in order to continue the simulation. If you want to do that, revive needs to be copied in revolt, and refcon needs to be copied in config in order to preserve information from the previous run. You need to be keeping copy of config, otherwise it will be overwritten if you just simply copy over it. So before we continue with some examples of what these files look like, we should talk a little bit about what are the DIL poly units. So there are some internal units because we only specify numbers in the files. But these numbers, according to where they occur in the file, mean something, and they bear some physical unit. So all the masses that we specify on particles are in Daltons, which is the mass of hydrogen atom. All the charges in protons, and the lengths that we specify are in angstroms. The time is always in picoseconds, and derived quantities such as force and energy are derivative of those. So the force will be Dalton times angstrom times picoseconds to minus 2, and energy will be Dalton times angstrom squared times picoseconds to minus 2, or which coincidentally comes to be 10 joules per mole. The pressure is expressed in kiloatmospheres for input and output purposes. In DIL poly, users have the freedom to define their potentials or potential bearing parameters, because potentials usually are represented by analytical form or tablet in a file. However, these numbers do mean something, and especially in the potential forms, they're energy-bearing parameters, and the users have to opt at the very beginning of the field file to specify what is the energy unit of those parameters. Essentially, the DIL poly internal energy units are 10 joules per mole. Parameters can be specified in electron volts, or kilocalories per mole, or kilojoules per mole, or Kelvin over Boltzmann. Of course, if you have a mixture of parameters for a mixture of molecules or various chemical types interacting between one another, you have to be consistent in using the same energy unit for the full system. So this is an example of what a control file looks like. Essentially, it provides a simulation control. It is free format. It is mandatory. If there is no file, there will be no simulation. And it's driven by keywords with some options and data specified at the keyword. For example, we can say that we want to simulate an ensemble isobaric, isothermal in the Mosaic-Hoover interpretation with temperature and pressure relaxations having those values. The file itself is very simple. It's in simple ASCII. It starts with a title line, and then in any order that the user wishes, they can specify temperature by using a keyword temperature and then giving some numerical value. They can say pressure, type of ensemble. If it's more complicated ensemble, they have to say what kind of form and what kind of relaxation times or friction, and so on, depending on how it's defined in the manual. How many steps the simulation will be carried out for, how many of those steps will be equilibration, whether multiple steps will be used, whether we have to scale temperature, this is this directive here, how often we print in the output, so we see that something happens during the simulation so we can stop it prematurely or continue satisfied with it. How often to print statistics, whether we calculate redistribution functions and so on and so forth. And then we finish with the finish word. This is a keyword that's very essential because then everything that's below it will be ignored by the parser. Essentially, the first line is ignored because it is for you. It bears the meaning of what you're doing in this simulation. Then the rest of the keywords are important. Empty lines are ignored, and lines with hashes are also ignored. So if you want to leave comments between the lines, you can start a comment with a hash. The config file, and of course refcon and cfgmin, which are very similar to it, they just have a few extra quantities that are inessential if you want to use those files as a restart file. Has this form. So the config itself provides the initial atomic coordinates, while refcon is usually the final one, and cfgmin for the configuration with the minimum energy. It's a free format. Essentially, the first line again is a title line. It is for your own usage to specify what this file contains. Then we have two numbers reflecting what is the data that the file contains, whether it's only positions, velocities, position, velocities, and forces. This would be the first number, which is the data level. So we have 0 data level on the positions, data level 1 positions and forces, and data level 2 position, velocities, and forces. The second number indicates the image condition. In this case, it's a general parallelepiped one. Of course, you can find more about it in the manual. And then it follows with 3 lines, each of one representing the vectors of the MD cell. And then follows the list of particles. And for each particle, we have type of particle, or a species of particle. This is a sodium 1. And we have a global index, which is specified here. And then we have 3 rows of numbers, each row representing a vector. In the first row, we have the position vector. In the second row, we have the velocity vector. And in the third row, we have the force vector. And then we continue this for all the particles in the system. Of course, Deal Poly 4 allows for these particles to be presented in any order, but Deal Poly Classic, it has to be specifically this order, so 1, 2, 3, 4, 5, and so on. And this file has to match very, very finely the config file, the field file. We will talk a little bit more about it later on. And all these numbers, as I mentioned previously when I talked about units, bear some meaning. So positions will be in angstroms, velocities will be angstroms over picosecond, and the force will be Dalton angstrom over picosecond square. To construct this file, some kind of GUI is essential. Writing it by hand is very, very difficult and cumbersome. For complex systems, you have to rely on GUI. We'll talk about it later on as well. So the field file, which of course is probably the most complicated file with the largest number of possible keywords, however very simple in nature, of course, this one. The field file is the one that contains the force field and contains something about the physical, chemical nature of particles, how they interact. And again, it starts with the title line, then the second line is the most important, which is units. In this case, we have chosen kilojoules per mole. This is an old option that's only available in Deal Poly Classic, neutral groups. I'm not going to explain about it. You can find more about it in the manual. Then we start with molecular types. Essentially, how many different kinds of molecular types we have in the system. In this case, we have just the one, and we give the name of the first one. In this case, the only one, SPC water. It is only for you in order to relate to this. It has, it bears some meaning to you For the software itself, it doesn't really matter because it enumerates them. Then it says how many instantiations of this molecular type we have, so how many molecules of water. We have 256 molecules, and then we say what the general type, what the type of molecule has in it. So in this case, it has an oxygen named as OW, a hydrogen HW. It also has O shells. So as we'll see later on, we use the core shell model, which is indicated here as shell. It also uses rigid body units, and when we specified all the intermolecular information about this molecule type, we say finish. And even though it is molecule type 1, we may have had more. For each molecule type, we have to say finish and then continue on. And at the end, we have to specify the van der Waals interaction and external fluid interaction. And again, the most important word would be close, beyond which the parser won't continue, it will just give control back to the main program. So here in this water molecule, we say that we have 4 atoms. The reason we say this is because the oxygen atom is represented by 2 particles, one for the core, OW, and one for the shell. What you may find a bit confusing is that we have only 1 hydrogen. Actually, that is not true. What happens is that this hydrogen occurs twice in order to collapse the entry, which is very useful when you have very big systems with lots of repetitions. We just specify on one row all the properties of the particle that has been collapsed, because there are many instantiations of it within the molecule itself. So we give the mass, then the charge of the particle, then we say how many occurrences if they're one after another. For the hydrogen, we have 2, and then we have a state of that indicates whether the particle is frozen or not. As I mentioned, we have the shell directive saying that side 1 and side 4 of this molecule are connected via spring with spring coefficient of 100 with these units here. We also say that in this molecule we have a rigid body unit. There is only one rigid body unit within this molecule. It's got 3 members, and the members of it are 1, 2, and 3. And then we say finish. We have finished with the intermolecular information. In this case, we have finished with all the intermolecular information because we have just the 1 particle. And then we continue with the intermolecular one. In this case, we have only van der Waals interactions, but of course, we may complicate matters and have not just van der Waals, but 2-body, 3-body, 4-body, or metal interactions. And on top, we can have external field. In this case, we say that we have 5 van der Waals interactions, and they're specified here between what types of particles, what kind of potential form. I can see all of these Leonard-Jones. So we have 5 van der Waals interactions, and these are the parameters of the interaction, sigma and epsilon. And at the end, we finish with close. Again, as I mentioned, we only give numbers, but these numbers have meaning. So the mass will be in Daltons, the charge in protons, and we have energy-bearing parameters, and then we'll have the kilojoules per mole dimensionality. So for small systems, we can write this by hand, but if we have a complicated system, again, we have to use a GUI. So the next file is the table file. If we didn't have, for example, here, no, we don't have intermolecular interaction, but okay, here in the van der Waals, if we didn't have the potential for interaction between the shells, in the Leonard-Jones form, we would have put the word table or TAB, which would have meant that the software, when everything is ready here, would have given control to a routine that will read this file and extract the potential and the force from the numbers that have been supplied. It has a simple functional form. Like in all files, we have the first line, that is the title line, and then we give the grid resolution, the grid length, and how many data points, and then we print the data points in a certain way. So we include two rows that are broken and continue until the number of data points is satisfied. The first row, then the third, the fifth, and so on will be the data of the potential, and the second, the fourth, and so on will be the data of the force times the distance. And the better model file, the TABM file, the structure is a little bit more complicated. If users are interested, they can read about it in the manual. But essentially, again, we have some strings, some integers, and some real numbers that are read and parsed. Again, it's conditional. It only happens when you use the embedded atom model. So we have three different keywords there: pair, embedded, or density, or more, depending on whether you use two-bound embedded atom model or extended embedded atom model. And these are values that specified only for the potential arrays, and the force arrays are reconstructed from those using numerical derivatives. The revolve file, as I mentioned, is the only one that is not in ASCII, and it's in binary, so it's not portable from one machine to another, depending on what the file system is like, whether it's big endian or small endian. It provides restart capability. It contains all the thermodynamic accumulators, redistribution function data, mean square displacement data, and other checkpoint data needed for the specific ensembles. And if you want to restart the simulation from where we left off, or finished previously, we have to copy it to revolve and be an input file, which will be the input file for the next simulation. The output file provides a job summary. It's a mandatory file. There's a user option that could specify that we don't want to produce the output file in a file, but we want to produce that summary on screen. However, this is again a file that's printed on the screen. It is formatted, so it's human readable, and the content is a summary of all input data that can be opted out, but usually it is not. And it contains all the instantaneous thermodynamic properties at selected intervals. The rolling average is displayed for all thermodynamic data, and of course at the end of the simulation the statistical averages. Some fragment of the final configuration is also displayed, and if the user has opted for redistribution function Z density, some information about this displayed as well. There's some estimate of the mean square displacement to the 3D diffusion as well. There's some extra data like timing data, conjugate gradient method data, relaxed shell model data. Because we use conjugate gradients in the relaxed shell model, we need to see how the cycles go. And a lot of warnings, and if the simulation comes to an abrupt end, it is usually in control manner and with an error report. The status file is the one that contains the statistical information of all the instantaneous quantities calculated by the package at regular intervals of time. These intervals can be augmented by the user from their default value, which is 10, and it comes in a human-readable form. Of course, the number of values in each segment is the same, and it may vary depending on what kind of ensemble we use, what kind of options have been specified. Essentially, we start with a title line, it reports what the energy units are, and then the first value in the next row would be what is the time step at which these instantaneous values are taken, which is number 10. And then we have 20, 30, and so on. This is the the cumulative time, and this is the number of values that follow before you go to the next segment. Of course, this number of values is always the same for all the segments of the same simulation. However, if you write your own software to parse this file, you need to know how many values follow in order not to read extra. Of course, this file is readable by the dual poly GUI, and certain of those numbers can be interpreted as temperature, pressure, volume. However, if you want to get more out of it, because the GUI is limited in what it can display, you will have to know what these numbers mean, and that is very well described within the dual poly user manual. All these numbers, again, they have some units attached to them, and when you know what the number means, you will know what the unit attached to it is. I mentioned that one of the optional files was the history file, and the history file is more or less a consecutive dumps of the configuration at certain intervals of time. It has some extra data that are attached to it. However, portions of it can be used, each frame can be used as a restart file if you're willing to do that manually. It's not a very difficult job, it is possible. Essentially, again, we start with a title line. We have level of data, image condition, and how many particles. And then for each frame, we start with a time step. So here it says time step 1, how many particles. Again, it repeats some of the information, level of information, image condition, and what is the time step. Then it gives the lattice cell vectors, row by row, and then it starts with the particles. So this is the first particle, which has a certain mass and charge, and then it has, depending on what the level information is, the position vector, the velocity vector, and the force vector. And then this is printed for all the particles in the system. The next time frame that needs to be printed is attached right at the bottom at the end of this time frame. Again, all these data have their own units depending on what is the quantity that the data represents. The redistribution function and the z-density data are printed in RDF.dat and ZDN.dat files. They're very similar. What they have is they have a title line. Again, we say how many different profiles or redistribution functions we have, how many points, and then for each of the elements that we follow here, the redistribution function, this would be between these two atoms. We have the grid of a distance, and then we have the values of density of a distance. So dual poly 4, as I mentioned, had a few extra files from the traditional dual poly files. We have the reference file that contains some reference structure to compare against. We have the defects file, which is the difference between the reference and the time frame at which we compare. And we also have this trajectory-like file containing each particle's square root of the mean square displacement and the instantaneous temperature on the particle. Let's talk a little bit about dual poly 4 performance. So the largest simulation we have done, which was test of concept a number of years ago, had 3 million particles. It's amazing that since last year we have started doing 200 millions on a regular basis on about 60,000 processors. But when the package reached a certain stage of maturity, we tested whether we could do something like 300 million particles on 1,000 processors. And in 2005, it took an hour to do this one-time step only simulation. So it took essentially about 59 minutes just to load up the configuration, and then it took about a minute to do the force evaluation and integration. And the fourth, the Coulombic evaluation, the eval summation, to a large bit of it. Of course, doing this nowadays would take about 10 to 100 times less, but it is still a significant expense to meet. In theory, this system that we simulated in 2005 as a proof of concept, it can be seen by the naked eye. Well, you have to have a very good microscope underneath it. So let's demonstrate what the hard scaling is for a certain system. One of the systems that I have been simulating myself is zirconite, which is a gadolinium pyrochlore system. And in this graph here, you can see what the speed gain is when we start simulating 2,000 processors and go to 16,000 various components, so the speed up in various components of the full MD cycle. So we have demonstrated what a perfect scalability would be, and we compare different components. This is the total MD time step. This is the linked cell evaluation, purely van der Waals forces, only the real part of the eval summation, and the reciprocal part of the eval summation. And we can see that the most costly component is the k-space evaluation here. The rest of the components are linear, and when we combine all of them, sum them up, we can see what the performance of dual poly is for this system between 2 and 16,000 processors, indicated by the red dashed dotted line, which is a fairly good performance. We have some tailing off at this large processor count. If we talk about weak scaling, which means that instead of having the same system size on different processor counts when we execute in parallel, we have the same system loads per processor, which means that if we have, for example, 1,000 particles on one processor, we will have 2,000 on two processors, 3,000 on three processors, and so on. In this case, in this graph, we demonstrate what the difference in scalability is, weak scale performance of dual poly for three different systems. And the systems have been chosen so that they, memory-wise and hello-wise exchange, have the same load on the package. However, their complexity of the force field increases. So the solid argon system only have short-range interactions. In the sodium chloride, we complicate matters, and on top of the short range, we include electrostatics, because the particles of the sodium chloride molecules are charged. And the single point charge water, we also include constraint solvers, which I mentioned earlier, are iterative in nature until all bonds, constraint bonds within the system are satisfied within a given tolerance. And we can see that if we had perfect performance by this software, we would have lied on the green dashed line. We see that when we start on one processor, we have approximately about between 20 and 30,000 particles, and when we move to about 1,000 processors, we have between 20 and 30 millions. However, the load per processor is still the same, and the memory demand per processor is still the same. We see that the three systems behave differently. So the one with the best performance with the solid argon, because we only have short-range interactions. When we include evalt, as we saw in the previous graph, you have some tailing off. This is because of the n log n scaling of the fast Fourier transforms used in the smooth particle mesh evalt. And if we include some iterative calculations, for example here due to the constraint algorithms, this tells off even more, because we have to send data between nearby processors for constraint bonds that are shared between processors. And we share more the more domains we have. It's only local, but it does take time, and evaluating those forces to return particles back to the given constraint length is expensive. We will see later on how we can improve that. It is possible. Let me just mention what the maximum loads are. Quite often people ask, how many particles can I do on one processor? Well, it depends how much memory you have per processor. So for example, if you have 1 gigabyte and you want to simulate only short-range interactions, you can load up to 700,000 particles per that processor. If you include the electrostatics, then you can, or electrostatics plus constraints, you can load approximately 200,000 particles per that 1 gigabyte of RAM on your processor. Of course, what I didn't mention is the red dashed line, which is a measure of what good performance is. Good performance means that you don't lose more than 25, a quarter of your performance when you double the number of processors. And of course, our performance is better than what good performance is. However, we can see that the more work we need to do, we have to pay the price, and there is some tailing off in that performance. So, talking about water and constraint iterative solvers, if we moved from constraints, where the red line here is now I7, which is water, presented by constraint bonds, if we move from constraints to rigid bodies, then our scalability improves immensely. This is because now we don't need to have all these local updates between processors who share constraints, because rigid bodies move as a whole, and there is little expense on the rigid bodies that we have to solve on top of the Newtonian equations of motion, the Eulerian equations of rotation, but this is extremely cheap in comparison to doing iterations. So we do a little bit more computation, but we minimize on communication. And something that's quite important, so if a software is very good in terms of how fast it does the job, for difference with ab initio methods, it is not only how fast we calculate something, it is also we want to show it, we want to be able to display this and work with it, extract some data of those trajectories. And dumping a trajectory can be a gigantic task. So serial reading and writing are more or less prohibitive. That is why in DIL Poly 4 we offer a number of I/O solutions. Of course, the best is the parallel I/O via MPI I/O that is shown here. However, the user can still opt, if they wish, in order to compare how fast that is, for serial read and write, and they can have parallel write via direct access or MPI I/O. Of course, if they use direct access printing, it is not a strict standard, and it may not work on all machines. However, this is the default, and it always works. There's also parallel read via MPI I/O Fortune, and for people that are interested in saving their trajectories in portable binary format, we offer serial netCDF. However, this serial netCDF is just using serial netCDF library, but the writing and the reading is done in parallel using NPI. What I need to mention extra is that there's some cost associated with reading and writing, and reading is slightly slower, usually by a factor of 2 to 4 than writing, and we have been able, with carefully chosen parameters, defaults for the parallel write with MPI I/O, to make sure that the cost of writing the system, dumping our configuration frame on disk, is more or less equal to a one-time step worth of calculations, which is very, very good. In the past, when we did that in serial, the cost was enormous, especially when we were trying to reach systems of the size of million atoms. But nowadays, it costs nothing. Essentially, if we execute 1 million system, 1 million particle system on 1,000 processors, And if your time step is, let's say, a fraction of a second, a tenth or a hundredth, this is as much as cost you to actually dump the data of that frame on disk. So we can not only do this science fast, but we can capture it fast too. So how do we obtain and build the DIL poly packages? Essentially for DIL poly 4, we still require a license, and there's a license facility following this legacy link, which goes to the right link. And why we need a license? Because we need to protect the copyright of the package which has been developed at Dasborough Laboratory over a long time. We also want to reserve the commercial rights, so if there's a company that wishes to exploit the package, they need to pay a small fee for it. And of course to provide some documentary evidence to justify the continued support that we received by the UK Research Council. It covers only DIL poly 4, of course. Registered users are entered on a DIL poly emailing list. Of course, they cannot opt out of it, but if they stay on the list, they will receive messages that outline whether there is a workshop or a conference, or there is a new release of the package, so they can update, because as it happens, the new features coming in, and sometimes some flaws or bugs are being corrected. So support is only available to UK researchers. However, there is a forum facility where researchers from other countries can help each other or talk to developers and ask about future features, or whether they're seeing the correct outcome of their simulations. Last but not least, there is a very detailed, interactive and self-referencing PDF user manual, about 300 pages, so there is everything in it. If you can't find anything, you can always, anything that you think is important to know about what the capability of the packages are, you get in touch with the authors or publish your request on the forum, so we can look at what you think needs improving. So how is DIL poly 4 supplied? When you register at the link, as I mentioned before, again you can see it at the top of the slide. This web registration, there is an email sent to you. You have to provide a valid email that outlines where you can download it, which is an anonymous FTP server, and what is the password to decrypt that file that stays out there, which you can later on unzip and untar. And successful unpacking will produce a Unix directory. And of course, the test and benchmarking data that are also available on the FTP site. You will see those sites later on. They're specified here. So this is the FTP site with all the information where you can have the manual and all the test cases. This is the forum where you can find help or seek help or help yourself other people. And for DIL poly Classic, this is the link. It can be found within the main site, but this is the link if you want to access DIL poly Classic directly. So the supply of DIL poly Classic is via a facility we use. It is called TCP Forge. There is no need to register. It's a BSD open source license. You can download the source from following these paths: TCP Forge projects, DIL poly Classic files, and DIL poly Classic, and you have to download this file. You can download earlier versions as well, and if you like, you can compare what has changed. Sources are in a tart and gzipped form. There is no encryption, and successful unpacking will produce similar directory to that of DIL poly 4. We will see in a second what it is like. And there are also test data which you can as well download from this source or from the FTP source. FTP server mentioned here. In order to download test cases and manuals, you don't need to access it anonymously. You can just use your browser. So if you unpack any of the DIL poly packages, you will come across a Unix-like structure that is more or less the same for the two packages. So there are a number of directories, the build one, which contains the make files, the source one that contains the source. So for DIL Poly Classic you'll have the DIL Poly source, and for DIL Poly 4 you will have the DIL Poly 4 source. Then you have an execute directory with a few scripts that you may find useful, but this is the directory where if you're successful compiling the source using one of the make files in build, you will have a binary file that is executable and you can use to run any system that you have in a DIL Poly format. There is the Java directory where there is a Java GUI source code. It usually comes precompiled. However, some users find that it doesn't quite work depending on what version of Java engine they have. It is very rare, but it happens. However, it is very easy to compile your own Java. You just need to have not just the Java virtual machine, but the Java development toolkit, which is again a free component you can download from some. There is the utility directory with a number of codes contributed by the authors and other users, which example codes of what you can do on certain systems and how you can do it. In DIL Poly Classic manual, there is a very good explanation about a number of those routines you can find there, which you can modify or use in any way you wish. And the data directory points with a README file to where you can find the data. As over time the number of test cases has increased, we keep that data on the FTP server rather than provide it with the source download. A few rules of thumb for whether you should run DIL Poly Classic or DIL Poly 4 and on what number of processors. Essentially, they're very different, DIL Poly Classic and DIL Poly 4, engineeringly. However, they should do the same job on the same system, but they will do it slightly differently, even though they will produce the same numbers and the same files. Due to the different parallelization they use, they have different advantages depending on what you can do and on how many processes you execute. So, if you don't have, if one of the packages don't have the capability that you're after, you just use the one that has it. If you simulate less than 1,000 particles, definitely you can do it with DIL Poly Classic. There is no need to go to DIL Poly 4 except if you want to go DIL Poly 4. If you have more than 30,000 particles, then DIL Poly 4 is more or less the package of choice. There's some restrictions. For example, if the ratio of cell width over cutoff is less than 3, then the performance of DIL Poly Classic will be better than that of DIL Poly 4. And you may think that it is better to use DIL Poly Classic rather than DIL Poly 4. It is your choice. And if you have less than 5 to 100 particles per processor, it is again DIL Poly Classic that should be your choice, because this is the regime in which DIL Poly 4 doesn't perform as well as when you have larger loads of particles per processor, because then you get into a regime, usually you get into a regime where you have less than 4 link cells per dimension for a domain, and then you fill the prefactors rather than the speed up that the link cell algorithm provides. So there are some rules of thumb for various systems for DIL Poly Classic. So if you simulate simple molecules without constraint solvers, then you better use 8 or less process for 10,000 atoms, 16 or less for 20,000 atoms, and so on. For simple ionic materials, this number can be doubled. And if you have shake, you should never go beyond 64 processors. Communication becomes a dominant component, and you won't get very good performance from DIL Poly Classic. For DIL Poly 4, the rules of thumb try not to have fewer than 3 by 3 by 3 link cells per processor. Of course, you will still see the speed up and you will still see that the package works, but your speed up compared with twice less or 5 times less number of processors wouldn't be linear. So you will be getting into a regime like when you press the accelerator pedal of a car, it cannot go beyond this speed, even though you put it on more processors, or the car will waste more fuel, but it won't go any faster. The second golden rule is just try not to have fewer than 500 particles per processor. With a traditional MPI parallelization, less than 500 or 100 particles is warrants that you have less than 3x3 link cells, and you don't get any performance out of it. And in the limiting case of having a one link cell per domain, beyond that, the package will just notify you with an error message that it is impossible to run. But that is a big extreme. So usually stay above 500 particles per processor. That is the rule of thumb for dual poly 4. So let's talk about assisting tools. We covered almost all the bases of what dual poly essentials and algorithms are like, and what it can provide you with. More information is of course available in the manual. However, when we looked at the input files, we mentioned a few times that it's impossible to construct such files by hand. To facilitate your workflow, you have to use some sort of tools. One of the tools is the Java GUI. Java is free. It will facilitate the use of the code on any platform. There are a number of selection of options of the GUI that you can use for control capability. You can construct your own input files. You can control or submit job on the local system you run the GUI on. You can analyze the output files, even though they may have been taken from another system. And the GUI is portable and easy to extend by the user if they wish so, and they don't find the functionality that has been developed by Bill Smith. So when you start the GUI, what you get is the control window. It has a number of files in the file menu, a number of options you can click on. You can open files, you can make files, you can execute, you can do some analysis on the status file or resolution function file from a simulation. There is the information button here on the panel. If you want to create your own file, you can use the editor, and when you launch it, you will see something like this. Of course, the editor can display something that has been already produced. However, if you want to create something yourself, you have to click on the editor button here in order to make this menu active. The row of buttons that are shaded. When you make it active, you'll have the center of the coordinate system, and then you can start adding, when you click on options, you can start adding various elements, and then you can connect those atoms together into bonds, angles, and so on, and actually make your system. After you've made it, you can put a box around it, and then you can save it in a config file, and you can be assisted with a few schemes like OPL SAA and Drying Field to create interactions for the system that you have constructed yourself. So it's got a number of available menus here that describe what the menus provide. And the analysis is probably the most important one, because after you've constructed the system, you have run it, you want to analyze some of the data, so it will take the status file, and it will look at static dynamic properties, it will do some statistics, and it will plot for you certain graphs. And this is what a usual menu looks like. This one is for the radial distribution function calculator. If you have a trajectory, it will calculate the distribution function for you. You can specify between what atoms. You can specify various numbers here in order to do the averaging for the distribution function. Another tool that has become very, very popular recently, it is developed by Chin Yong at Dasbury Laboratory, is DL Field. DL Field has been specifically designed for users, and especially for biochemistry users of dual poly, to construct files, input files for dual poly, starting from protonated PDB file, protein data bank file, which gives the data in X, Y, Z. So DL field is essentially used as a black box, starting from a protonated PDB file. Of course, the PDB files are not usually protonated, but you can do the protonation of those using a number of free software packages. And in the field file control file, you can specify what kind of interpretation you would like your force field to be generated in. You can have AMBA scheme, child scheme, OPL SAA, PCFF, Trading film, field, or Charm 19 for United Atom model. Recently, we have included inorganic fields in the package, and it can account for core shell polarization as well. There's elevation features and auto-connected feature for mapping complex random structures, such as gels and random polymers. And of course, there is some input units freedom and molecule rigidification if the user wants to use specific functionality of DL poly that is not usually default when you transform from PDB into DL poly format. Essentially what the package does is, starting from something like this, which is the sodium oxide dismutate protein, it will generate a large field file containing about 4,500 atoms with 19,000 two-body interactions, 8,000 three-body interactions, and 13,000 four-body interactions, and 730 van der Waals interactions in the system. It is very powerful. It has a very nice manual as well, so I can learn to work with it. If you wish to display your trajectories, one of the packages we recommend is VMD. It's a free software package for visualizing electrodynamics data. It can do more than this. You can see what the website is. It is very useful for doing snapshots and making movies. And there is default plugin supplied with the package that makes DL poly history files readable. You just have to opt for what kind of version of DL poly file, DL poly history file you're specifying, whether it's version 3 compatible or version 2 compatible. It can also display other files like XYZ or PDB format, so it's a very, very powerful visualization package. If you want to find out more about DL poly, you should visit our website here. If you want to find the test cases, manuals, and all the information that you need about the package, you can go to the FTP. If you want to become a developer yourself, these are the development directories of CCP Forge. And if you want to be part of the community, you can join the forum. This is the link to the forum. If you wish to do some of the exercises that we've put out there on the web for you to train, you should visit the last link. Thank you very much.